Hello and welcome. My name is Amr Kamil and I'll be talking about optimization of asynchronous communication operations through eager notifications. This is work done with Dan Bonachea under the Pagoda project at Lawrence Berkeley National Laboratory. This work was done in the context of UPC++, which takes a library-based approach to providing a programming system for high-performance computing. In particular, UPC++ leverages standard C++ template metaprogramming, as well as a lower-level GasNet-EX communication library. GasNet-EX gives us one-sided communication operations that are built on top of the network hardware, utilizing features such as remote direct memory access, as well as providing an active message abstraction on which UPC++ remote procedure calls are built. GasNet-EX enables us to run across a wide variety of machines from laptops to supercomputers. The library-based approach gives us straightforward interoperability with a variety of other models, including MPI, as well as on-node models such as OpenMP and CUDA. The core features of UPC++ are RMA and RPC. RMA, or remote memory access, encompasses one-sided communication operations, including get, put, and accumulate to locations in other address spaces. RPC, or remote procedure call, involves moving computation to the data. The main design principles for UPC++ are geared towards performance. For instance, all communication is syntactically explicit, so that it's clear to the programmer where communication happens. All communication is asynchronous, and we have abstractions such as futures and promises to manage that asynchrony. And then internal data structures as well as user-facing ones are designed to avoid unnecessary replication so that they can scale to thousands of processes. UPC++ is an example of a PGAS, or Partition Global Address Space system, in which individual processes have a private segment of memory that only they can access, as well as a shared segment of memory that's accessible to other processes. The union of these shared segments is called the global address space. Now, it's common to have multiple processes co-located on the same node, in which case we can just use standard C++ pointers to refer to memory. However, to refer to an object that is on a process on a different node, we need the abstraction of a global pointer, which encapsulates both the affinity or owner of the particular object, as well as its location in memory. Global pointers are the mechanism through which RMA occurs, and they allow the programmer to manage locality. Now, this particular work is focused on node accesses using RMA through global pointers, which we want to make as efficient as possible. These one-sided communication operations are asynchronous in UPC++, where the completion is separated from the initiation. In the code example here, we have a global pointer to some int object, and we launch a one-sided get on it. And so what we get back is a future that encapsulates the result, as well as whether or not it has arrived. We can then go ahead and do some unrelated work. And then when we're done with that, wait on the future, which actually assures its completion, the completion of the underlying get, and returns us back the value as a result. After that, we can go ahead and launch another operation, in this case a put, to that same memory location. Now, a put doesn't return a value to the initiator, so what we get as a result of initiating a put is a future that represents just the completion of the put without any values. In general, a future holds some values and a readiness state, whether or not the underlying operation has completed. With futures, we can actually construct an entire directed acyclic graph of dependencies. For instance, we can chain a callback onto a future using the then method and a function object, and the result is a new future. We can conjoin multiple futures together with WinAll, which takes a number of futures and gives us back a single future that encapsulates all the results and readiness of the input futures. In this code example, for instance, we launch two args from different sources, one that produces an int and the other that produces a double. We then conjoin them together, which gives us back a future that represents both the int and the double, as well as their readiness. We then attach a callback to that, which takes those two values and multiplies them together and then launches a put of the result to some other target. And so what we get back from there is a future representing that put. But because this put depends on all of the previous operations, it actually encompasses completion of the entire DAG of operations, and we only need to wait on that one feature to ensure that all of them are complete. Features are one mechanism for working with asynchrony, but there are others as well. In fact, UP++ communication operations actually take a completions argument that happens to be defaulted to requesting a feature. When a feature is requested, the call actually internally allocates a promise, which represents the producer side of the operation, and it's where the values are supplied and where the operation is marked as complete. And then the call returns back to the user a feature that represents the consumer side of that operation. Rather than having the library internally allocate a promise, a different form of completion actually allows the user to provide their own promise, which they can reuse over multiple operations and thereby avoid the internal allocation. In addition, there are other kinds of completions like local procedure calls, delivering a remote procedure call to a target, and so on. And the user can even ask for multiple notifications of different types for the same operation. As far as delivering notifications, UP++ has adopted a progress model that avoids hidden threads. This allows the implementation to be lightweight and minimizes synchronization. Prior to our work, notifications were actually required to be deferred until the next call into the progress engine, which includes calls such as wait, even if the actual access completes synchronously. So this results in consistent semantic behavior in the on-node as well as the off-node case. The code here, for instance, launches an RPut to a global pointer, which may be to on-node or to off-node memory, and then it attaches a callback to the result, and then it goes and does some other work. With deferred notification, we're ensured that the second code block will execute before the first one, even if the RMA completes synchronously. So this was a simple semantics, but we found that it actually doesn't provide the best performance when it comes to on-node operations that do complete synchronously. The downside of deferred notification is that it can incur significant overheads for on-node accesses relative to the low cost of the access itself. In particular, it forces the notification to go through the progress engine, and for future-based notification, it forces a promise cell to be allocated by the library to hold the readiness state and any values. To get around this, what programmers might do is what we refer to as manual localization, where they check whether a global pointer is actually directly addressable, and if so, do the direct access. If not, then launch an RMA. This manual localization leads to code bloat, in particular if we have a number of global pointers with independent locality properties, then we end up with combinatorial explosion of the code size. It also duplicates the locality check that is already in the runtime. To address this, we introduced a new form of eager notification in an experimental version of UP++ that's now actually been incorporated into the most recent release. What this eager notification does is that if an operation completes synchronously, then it immediately signals notification. We introduced new factory methods for requesting either deferred or eager notification, as well as a macro to control what the default is. If the macro isn't defined by the user, then we default to eager, since that provides the best performance. To maximize the performance of eager notifications, we also made several optimizations to features themselves. For instance, we realized that features that don't encapsulate a value, so a feature type with an empty template argument list, those that are ready are actually semantically equivalent with each other. So if a communication operation completes synchronously and doesn't produce a value, then rather than allocating new internals, it can just reuse pre-allocated internals to represent the resulting ready valueless feature. Along the same veins, when conjoining multiple features, if the resulting values and readiness all come from a single feature, then that one feature is semantically equivalent to the result. In the code example here, we have feature one that encapsulates an int and a double and isn't ready. and that gets conjoined with future 2 and future 3, which don't have values and are ready. So conjoining them together, the values and readiness all come from future 1, and we can just copy it over as a result. Combined, these optimizations significantly improve a particular pattern of combining the results of multiple operations in a loop into a single feature. In this example, for instance, we start off with a ready valueless feature, and then we launch a number of rputs and conjoin it with that original feature to give us a result that encompasses the completion of all the rputs. If the rputs actually complete synchronously, then there's no internal allocation and the result is just the same original feature. To measure the impact of eager notifications as well as our optimizations, we compared 3 versions of UPC++, including the most recent release prior to this work, which we used as a control to ensure that we didn't introduce any performance regressions, our version using deferred notifications, and our version using eager notifications. We looked at 3 benchmarks, a set of micro benchmarks that measure the performance of individual RMA and atomic operations, implementations of the HPC Challenge random access benchmark using RMA and atomics, and a half approximate maximum weight graph matching application. Since we're concerned primarily with the overheads for on-node performance, we did all our experiments on a single node across 3 different systems using 16 processes. Due to time constraints, we'll only look at the Intel results here. The other results are in the paper, and we saw similar results as we did for Intel. The micro benchmarks measure performance of 64-bit data transfers using either RMA or atomics between co-located processes on the same node. Each experiment timed 10 million operations, initiating an operation and then immediately waiting on it before moving on to the next one. We repeated the experiment 20 times and took the average over the top 10. What we saw was that there was no regression between the earlier version of UPC++ and our version using deferred notification, and in fact, there were significant improvements due to orthogonal optimizations. With respect to eager notification versus deferred, we saw improvements ranging from 46% for value-producing atomic fetch add all the way up to 92% for put. For the GUPS benchmark, which does randomized fine-grained updates on a distributed table, we have several versions using either RMA or atomics, and with either future-based notification or promise-based notification. What we see here is that for promises, improvements ranging between 3 to 15% for eager notification over deferred. For futures, much larger, 150% to 300%. And the reason for this is because in addition to skipping the progress engine, the feature-based versions benefit from all the optimizations that we did for ready futures and conjoining them. Our third benchmark is a graph matching algorithm written by Sayan Ghosh, one of the developers for the Exagraph project. So this is code written by a third party that we didn't modify in any way. As written, the code optimizes updates to the same process, but for co-located processes, it uses RMA. We ran experiments with 4 graphs from the sweet sparse matrix collection with varying levels of locality of the edges. Additionally, we randomly generated a graph that has most of the edges between nearby vertices, but with about 13% of the edges between random vertices. Here are the results. One thing to note is that speedup is limited by how much of the application time is spent in communication and how many of the updates are to other processes where RMA is used. What we see here is that for graphs that have some number of updates to other processes, improvements in the 5% range, up to 11% for the YouTube graph that has a higher fraction of updates to other processes. The result is that eager notification can actually improve the overall performance of an application, as we see here. To summarize, one of the benefits of the PGAS model is that it enables the same code to operate on both on-node as well as off-node memory, resulting in good productivity and maintainability. For performance, PGAS systems need to ensure that the performance of on-node operations is as efficient as possible, and asynchronous systems in particular need to ensure that the mechanisms for asynchrony only minimally impact performance. In the case of UPC++, we found that eager notifications provide significantly better performance than deferred notification on-node operations, up to 10x for RMA operations, 3x for a GUPS benchmark, and 11% improvement for a full graph matching application. We're continuing to work on improving the UPC++ implementation, both for on-node as well as off-node performance, as well as providing new features. Thanks to our funding source and to our computing center partners, and thank you all for attending.